very important mathematical technique which is heavily used in courses in economics is the derivation. By derivation, I mean a technique with which you can easily characterize the behavior of a function. Let us see first an example. As we just saw, a quadratic function might be very useful, for example, to describe the relationship between the consumption of a good X and the benefit which you can gain from consuming that good. And we already saw that initially the effect on the total benefit or utility would be positive, after which a saturation point is reached, and then the effect of any further units of X consumed is negative. Now we would like to characterize the behavior of this function. Let's assume that at start, at this quantity of x, x0, I know that at this quantity the value of the function will be y0. Or I could also say that this is f of x0. Now I may increase this x0 by a certain quantity to x1. And that means, of course, that at this particular point, the function will take the value of f1, which could also be written as f of x1, of course. Now, one way to characterize this relationship would be just to draw a line connecting these 2 points and looking at the slope of that line. That slope would be then a measure of the average consequence of increasing x by a certain quantity. This line is called the second line, and the slope of the second line I will just call slope. So how could you mathematically write out this slope of the second line? The slope would be nothing else than the ratio between the change in y and the change in x. So the slope would be then y1 minus y0 over x1 minus x0. Or I could also write this as f of x1 minus f of x0 over x1 minus x0. Let us introduce now a different notation. Let us call x1 minus x0 delta x, where delta is the usual notation for a change. From this one, you can already see that x1 could be written simply as x0 plus delta x. So it would be possible, and even for our future purposes, it is better to write the slope as the function's value at x0 plus dx minus f of x0 over delta x. So this is something which is, in essence, very similar to a first derivative. Nevertheless, this is a very imprecise tool to analyze this function. Why? The problem is that here delta x was a relatively large number. So what if I increase delta x? For example, there is an x2 here, and I'm interested in the effect of such a large delta x, such a large change in x on y. Now you would get another prediction for y. This would be another value of the function, namely y2, and if you connect these two lines, then you will see that the slope will be smaller. If you go even further, and for example you will look at x3, then here your function would take a value of y3, and if you were connecting your initial point with this particular point, then you would find a negative slope. So actually, depending on the delta x you choose, you will get a very different characterization of the function. Initially, it is a very steep function. Then it becomes a relatively flat function, and you will get a decreasing function if you choose a too large delta x. This is obviously because delta x is chosen as a very big number. So how would it be possible to get a slope for every single point of the curve or function? Now this would be possible if we decrease delta x to a very small but non-zero number. So when when dx goes to 0, then actually we have dx. So delta x is now replaced by a different notation, dx. And when we use dx, that will always mean that the increase in x will be very small. How small? Well, you don't really have to define that. The only thing is that this is a very, very small number, but not equal to 0. Why? Because, of course, division by 0 is still non-defined. So you want to avoid that. In this case, you could actually say that because dx is so close to 0, for this reason, when you calculate the slope of the second line for this very small change, it could be actually also treated as if it was the slope of the function for that one particular initial point. So here is our function. And now what we are going to do is that we start at point x. And then we are going to choose a very small dx. And this will be x plus dx. And as you can see, if I connect these 2 points, then basically what I'm getting is a line which just touches this function at x. So a given value of x. This is what we call a tangent. And the slope of the tangent line is going to be our measure of the slope or curviness of the function at a certain level of x. And this is the first derivative of y. Let's see, or f of x, let's see how we could describe this. So you can see that here you have x, and here I'm going to already use the notation that this is the first derivative of y with respect to x, and this is one notation for that. So you can see that initially there is a very steep curve here, so that means that we should start with a very large slope. And as we increase x, so you are going to get an increasingly flatter line. And at the point of saturation, the slope of this line will be 0. So that means that we start with a very large value, which will go down. And after a while, when consuming more of x would be harmful, we get a negative slope. So actually, what we find here is the first derivative of a function is a function itself. So what we really did here was the following. We said that we define a new number, a new slope, which is nothing else than this object here. So f of x plus dx minus f of x over dx, and this is where you can see that dx cannot be 0, but it will be, of course, close to 0. But how could you calculate then the first derivatives of certain functions? Let us look at those functions we discussed in the previous clip. So here we have a y being equal to fx, which is just simply a constant. Question is, what is f of x prime? That is the first derivative of f with respect to x. Now, using what we have here, we can write here that, okay, if f of x is a, then that means that f of x plus dx must also be a, because at the right hand side there is no x. So that means that f of x plus dx is a, and f of x is also a, and this is divided by delta x. And this is of course 0 over delta x, or 0. That means that the first derivative of constant is 0. But if I have a function like this, again we can then use the above formula. So what is the value of this function when we have the function's value at x plus dx? Now that would be then a plus b times x plus dx, and then we would just subtract a plus bx from this. And this is divided by dx. Now, if you split these parentheses up, then what you have here is the following: a plus bx plus b times dx minus a minus bx. And you can see already that these two expressions are going to cancel each other out, and now you have b times dx over dx, which is just b. So as you can see, the slope of a line will be a constant, and this is also logical. This is what you see on a graph. Simply, the line will not change its flatness, its slope. Now, how about our function, which we used earlier, the quadratic one? Now, in this case, you have that y equals a plus bx plus cx squared. Now, in order to solve this first, you should realize that taking first derivative is actually a linear operation. That means that the first derivative of this is nothing else as the first derivative of, and this is also another notation, so dy over dx is another notation for the first derivative. So actually what you can do here, that you just look at each component of this sum. And here you would have d bx over dx, and here d cx squared over dx. And what you will find that the first derivative of a constant with respect to x is 0. Here you can see that the first derivative of bx with respect to x, this is something that we found here already, is b. So b will come here. And for this one, we are going to use a rule. First of all, this can be written as c times dx squared over dx. Why? Because if you multiply a function by a constant, then it will remain there as a multiplier even if you take first difference. The second thing is that whenever you have a function like x to the power of r, so when this is your function, then the first derivative, this will be r times x to the power of r minus 1. So you take the exponent, you make it into a multiplier, and you reduce the exponent by 1. So what is then the first derivative of x squared over dx? It is then the same as here, but r is no 2. So we will have 2 times x to the power of 2 minus 1, which is just 1, and that's why it is just 2x. So b plus c times 2x is going to be our solution. How about this function here? Logarithm of x. Now the first derivative, and this is something we will not derive, of this is just 1 over x. So let us have some examples and practice a little bit this. Let's assume that you were said that a certain function looks like this. And now you should take the first difference of it. How would you do that? Well, if I just take the first derivative of y with respect to x, then basically what I do is that I can just treat these added components individually. So we have the first derivative of a times x with respect to x plus the first derivative of b times the logarithm of x over the x, so the first derivative with respect to x. And now we can look at this. First of all, this will be just a constant, so it can be brought in front of the derivation, and you have a times dx over dx. Now, that's because the first derivative of x with respect to x is 1. Plus, you will have here b, and then d, and then x over dx. So, based on this, we can already say that because the first difference of x with respect to x is just 1, this becomes a plus b times the first difference of logarithm of x with respect to x, which is just 1 over x, or you could write this like this. Let's use now the power rule again. So if f of x can be written as x to the power of r, then the first derivative, which you could just call dy over dx if you want, or dxr over dx. These are equivalent notations. Yeah, and then I write it here that this is of course y. That is r times x to the power of r minus 1. This is something we used earlier. But now let me then introduce something more tricky. What if y equals 1 over x? No, we haven't learned any rule about this, did we? Well, actually we did. Just did, because 1 over x is x to the power of minus 1. So we actually have the same function like this. And you only have to use this rule. So r is minus 1. That will become here a multiplier. And this minus 1 will be multiplied by x, where minus 1 should be taken, which is minus 2, and this will give you minus x to the power of minus 2, or minus 1 over x squared. So, as you can see, with these handful of rules I showed you, you can already achieve a lot. How about another function? Now, to make this a little bit more lifelike, I will stop using this notation of y and x. So, let's assume that we have a firm, and this firm produces a certain quantity of a good, Q, and we use different inputs. One input could be the amount of capital, and this is going to have a certain impact through this power function on Q, and this is going to be then the amount of labor we use, which is going to have an exponent equals beta, and you can think this alpha and beta being both positive numbers, bigger than 0 and less than 1. The question is, how would my output react if I hired another worker? Now, this question could be reformulated like this. So, what is the change in Q if I increase my labor force by a small quantity? When you do this, actually you take the first difference of a multivariate function, because instead of a single x, you have here two different x's, because k and l are both some kind of explanatory variables or arguments of the function. So when you take the first difference with respect to L, then you should always treat the rest of the factors as if they were constant. So in this case, you can immediately write k to the power of alpha as a constant multiplier. And then you would only use here the rule that we just discussed, and that would mean that first difference of this with respect to L is nothing else than beta times L to the power of beta minus 1. So you could just write this here. And this is the first difference of the output with respect to L. And actually here you saw a production function, and this is what we would call the marginal product of labor, and we will discuss this later. Now, these concepts are very important, and not only for your further studies, but generally you should now understand why we actually use so much mathematics, because it can be used to identify and calculate those changes, those effects which play a central role in economics. But the essence of this is practice. There is no better way to learn mathematics than to practice and make some problems which you can find on the internet, for example. So there are many very good videos around YouTube, and of course you can very easily find tutorials where you can further practice the use of derivatives. Another thing is to explain why we would like to use first derivatives besides calculating some kind of reaction of one variable to the change in some other variable. And there is an explanation for that. Sometimes we want to optimize. So we have a function and we want to find that at which value of x, y is going to be maximized. So let us go back to the early example where you have here y and you have here x. And there is a quadratic relationship between these two. And I'm interested in the amount of x here at which I would get just the maximum possible y. So this could be, for example, the tax rate, and this could be the tax revenue. So at which tax rate would you get the maximum tax revenue? And this curve may be also known to you already. This is called the Laffer curve. So how would you find this? What is then the revenue maximizing tax rate? Now, if you knew that this is a function which is quadratic, and maybe theory tells you that it must be quadratic, then you can make use of the fact that the tangent line will have a zero slope, so it will be a horizontal line only when there is a maximum point of this function. Because, again, you have, for every single x values, a different slope of the tangent. But here, at the saturation point, at the maximum, the slope of this tangent will change from positive to negative. So there is a maximum point where it should be just zero. And of course, if you go further, then your total tax revenue is going to decrease, and that is shown by the negatively sloped tangent lines. So if I take the first derivative of this function and I look at that value of x, which makes that first derivative equal to 0, then that x value should somehow make y to reach its maximum or perhaps its minimum, but no, you can see that this is going to be a maximum. This point is often called the stationary point or inflection point. There are several expressions for that. Let us just go for stationary point, so this would be a stationary point. Now the origin of this expression is not really important for us, so that means that y is at its maximum or perhaps its minimum, we don't know that for sure, when the first derivative of y with respect to x is 0. So in this example, it might be that we have y equals a plus bx plus c times x squared. And if you take the first derivative of this, then this will be b plus 2 times cx, as we saw earlier. So the first order condition for this maximum or minimum, and this is what I will write here, first order condition, you don't need to really know this better for now, only if you really decide to do economics as major. So this should be equal to 0, and then this is indeed the stationary point. Now let's see if b plus 2 times c x prime equals 0, that means the 2 times c x star will be minus equal to minus b. So I just subtracted b from both sides. And now I have to divide by 2 times c, and then I get an expression for the stationary point. So let's see, let's assume that b is 10 and c is, for example, 0.5, minus 0.5, okay? Then, for example, if you have a function with such values for the parameters, then you will know that there will be a maximum point for y at a certain value of x, and this value will be minus 10 over minus 0.5. So I just use this result here, and that would then be 20. So we know that when x is 20, then y is going to reach its maximum point.